Comparison: triangle similarity versus general polygon similarity. Hello everyone. Let's begin our lesson today by looking at the fundamental concept of similarity. When we study geometry, we use the term similarity to describe figures that share the exact same shape, even if they aren't the same size. Think of it like zooming in or out on a photograph. The image stays the same, but the dimensions change. Now, while this general definition of similarity applies to all polygons, whether they are quadrilaterals, pentagons, or even hexagons, we are going to discover something very interesting today. As we move through the lesson, you'll see that triangles are actually a special case. They possess unique mathematical properties that make proving their similarity much simpler and more efficient than proving the similarity of any other polygon. Keep this distinction in mind as we dive into the specific rules for general polygons in the next slide. 1. Similarity in general polygons. When we move beyond triangles and look at general polygons, things like quadrilaterals, pentagons, or even hexagons, the rules become a bit more strict. For these two polygons to be considered truly similar, you cannot just check one property. You must satisfy two distinct conditions, and both of them must be true at the same time. The first condition is the equality of corresponding angles. This means that every interior angle in the first polygon must have a matching angle in the second polygon that is exactly the same size. However, having equal angles isn't enough on its own for these shapes. That brings us to our second condition, the proportionality of corresponding sides. This means that if you compare the lengths of the corresponding sides, they must all share the exact same ratio. Now that we've established the basic definition of similarity, remember, it's all about having the same shape, even if the size differs. Let's look at how this applies to more complex shapes. As we are about to see in the next slide with our example of rectangles, if you only satisfy the angle condition but fail the side ratio condition, the shapes are not similar. So, keep both of these requirements in mind as we move forward. Example: the case of rectangles. Now, to really grasp why we can't just rely on angles alone for all shapes, let's look at a concrete example on this slide. We are going to compare two rectangles, which are a type of quadrilateral. Imagine we have rectangle A, which has a width of 2 centimeters and a length of 4 centimeters, and then we have rectangle B, which has a width of 2 centimeters but a longer length of 6 centimeters. First, let's perform our first check, the angles. Since these are both rectangles, we know that every single interior angle is 90 degrees. Because the angles match perfectly, we can say that the first condition, the equality of corresponding angles, is fully satisfied. However, we cannot stop there. We must now perform our second check, the proportionality of the sides. Let's look at the ratio of the widths. We have 2 divided by 2, which equals 1. But when we look at the ratio of the lengths, we have 4 divided by 6, which simplifies to 2/3. As you can see, 1 does not equal 2/3. Because these ratios are different, the sides are not proportional. Therefore, our conclusion is that even though the angles are identical, these two rectangles are not similar. This perfectly illustrates the point I made in the previous slide. For general polygons, having equal angles is not enough. You must also have proportional sides. This sets the stage for our next slide, where we will see how triangles are a very special exception to this rule. 2. The special case of triangles. Now, we've just seen with our rectangle example that for general polygons, checking angles isn't enough. You have to check the sides too. But here is where things get really interesting. Triangles are actually a special case in geometry. Unlike the quadrilaterals or pentagons we just discussed, you don't actually need to verify both conditions to prove that two triangles are similar. In the world of triangles, the two conditions are linked. If one condition is true, the other is automatically guaranteed to be true as well. Let's break this down into 2 specific directions. First, let's look at how the angle condition implies the side condition. This is what we call the AAA, or angle-angle-angle, criterion. According to Theorem 6.3, if you can show that the corresponding angles of 2 triangles are equal, for instance, if angle A equals angle D, angle B equals angle E, and angle C equals angle F, then you don't need to do any extra work on the sides. It is mathematically guaranteed that the corresponding sides will be in the same proportion. Specifically, the ratio of side AB to side DE, side BC to side EF, and side CA to side FD will all be exactly the same. On the flip side, we can also go from sides to angles. This is our second direction, often referred to as the SSS, or side-side-side criterion. According to Theorem 6.4, if you start by proving that the corresponding sides are proportional, meaning the ratio of side AB to side DE, side BC to side EF, and side CA to side FD are all equal, then the angles are automatically locked into place. You can be certain that angle A will equal angle D, angle B will equal angle E, and angle C will equal angle F. So, as we move into our summary table in the next slide, keep this shortcut in mind. For triangles, one piece of evidence is enough to prove the whole story. 3. Summary comparison table. Now that we have explored the specific rules for general polygons and the unique properties of triangles, let's bring everything together with this summary comparison table. This is a great way to visualize the fundamental differences we've just discussed. If we look at the first row, which focuses on the angle condition, for general polygons like the quadrilaterals we looked at in the previous slide, you cannot skip any steps. You must manually check that all corresponding angles are equal. However, for triangles, the angle condition is sufficient on its own. This means if you find two equal angles, or what we call AA or AAA, you've already done the work. Moving down to the second row, let's look at the side condition. Again, for general polygons, you must check that the sides are proportional. But for triangles, the side condition is also sufficient on its own. If you can prove the sides are in the same ratio, what we refer to as SSS, the angles will follow automatically. Finally, looking at the requirement row, this summarizes our main takeaway. For general polygons, both conditions, the angles and the sides, must be true simultaneously to claim similarity. But for triangles, the beauty of geometry is that either one single condition is enough to prove similarity. Keep this distinction in mind as we move into our next slide, where I'll show you how engineers actually use this shortcut in real-world structural design. 4. Real-world application, structural engineering. Now that we have understood the theoretical difference between how we treat general polygons and triangles, let's look at how this mathematical principle actually works in a real-world scenario, specifically in structural engineering. Imagine an engineer who is tasked with designing a triangular support brace for a bridge. This is a perfect practical application of the concepts we just discussed. First, let's look at step 1, the design. To ensure the brace fits perfectly within the bridge's existing architecture, the engineer decides that the internal angles of the triangle must be exactly 30 degrees, 60 degrees, and 90 degrees. Next, we move to step 2, scaling. In engineering, you rarely build the full-size structure immediately. The engineer first needs to create a small-scale model of this brace to test its stability, and then eventually, they will produce the full-sized version for the actual bridge. Finally, let's look at step 3, the similarity advantage. This is where the special case of triangles that we talked about in the previous slide becomes incredibly useful. Because the engineer is working specifically with triangles, they only need to ensure that the angles are exactly 30 degrees, 60 degrees, and 90 degrees in both the small model and the large bridge. They don't have to go through the tedious process of manually calculating the ratio of every single side to ensure the shape is preserved. As we learned earlier, the laws of triangle similarity guarantee that if those angles are identical, the sides will be proportional automatically. This efficiency is a huge advantage in complex engineering projects. Now, let's wrap everything up with our key takeaways. Key takeaways. First, let's revisit the rule for general polygons, like the quadrilaterals or pentagons we looked at earlier. Remember, for these shapes, you cannot take any shortcuts. To claim two polygons are similar, you must satisfy both conditions. You have to prove that the corresponding angles are equal and that the corresponding sides are in the same proportion. One without the other isn't enough. Now, as we saw in our comparison, triangles are a special, much simpler case. Proving triangle similarity is easier because the two conditions are interdependent. This means that if you prove the angles are equal, the sides will follow suit, and if you prove the sides are proportional, the angles will automatically match. They are linked together. Because of this unique property, you don't need to check everything. To prove two triangles are similar, you only need to satisfy just one of the specific criteria. You can use AA, which is angle-angle, AAA or angle-angle-angle, SSS, which is side-side-side, or SAS, which stands for side-angle-side. All right, let's bring everything we've discussed today together into a final summary. As we will see in our next slide, it is very important not to let this easier rule for triangles trick you into making mistakes when you are working with other shapes like quadrilaterals. Common mistakes. First, be very careful not to apply triangle rules to quadrilaterals. It is a frequent mistake to assume that if two quadrilaterals have equal corresponding angles, they are automatically similar. As we saw earlier in our example with the two different rectangles, having equal angles is not enough for four-sided shapes. You must also ensure the sides are proportional. Don't let the simplicity of triangles trick you when you are dealing with pentagons or hexagons. Second, make sure you aren't confusing similarity with congruency. While they are related, they are not the same. Remember, similarity involves a ratio. It's all about scaling a shape up or down. Congruency, on the other hand, is much stricter. It requires the sides to be exactly equal, which is essentially a ratio of 1:1. Finally, always be precise with your vertex correspondence. When you write a similarity statement, such as triangle A, B, C is similar to triangle D, E, F, you must ensure that vertex A corresponds to D, B corresponds to E, and C corresponds to F. If you list the vertices in the wrong order, you are technically making a mathematical error, as you are implying a relationship between the wrong parts of the shapes. Now, before we wrap up today's lesson, I want to highlight a few common pitfalls that students often encounter when working with similarity. Paying attention to these will help you avoid losing marks on exams. Keep these points in mind, and you'll be well on your way to mastering geometric similarity. Great job today!